Hello and welcome to this A-level chemistry video about optical isomerism. We're going to take a look at what optical isomerism actually is and also how you draw optical isomers. We're going to look at what it means to be optically active and then consider this from the point of view of racemic mixtures and what they are. And last of all, we'll finish by looking at how we can tell whether or not a molecule is optically active. A quick overview of isomers here. Isomers takes its name from Greek, where iso means equal and mer means parts. There are two different types of isomers. There are structural isomers and stereoisomers. Structural isomers are where you have got the same numbers of each type of element present in a compound, but they have a different organisation. There are three types of structural isomers. There are chain isomers, and that's where the carbon skeleton has branches, and it might be a chain of 4 or a chain of 3 with a branch in the middle. And then there are position isomers, where the functional group, for instance a bromine atom, might be in different positions along the length of a carbon chain. And finally, there is functional group isomers, where the atoms themselves are reorganised in such a way that the functional group is different between one isomer and the next. Stereoisomers are where you have got the same atoms and you've got the same structural formula. So in other words, the atoms are in the same sequence in a molecule, but they actually have a different spatial arrangement. There are two types of stereoisomer. There is the EZ isomerism that you will typically encounter in alkenes because of the restricted rotation. But you can also get EZ isomers in things like cyclic compounds and in transition metal complex ions. The last type of stereoisomerism is called optical isomerism, and that's where, again, you have got the same structural formula but a different arrangement in space, where you end up with two isomers that look very much the same, but they're actually non-superimposable mirror images of each other, and that can lead to different properties. Let's look now in more detail about what optical isomers actually are. As I've said, optical isomerism is a type of stereoisomerism, and that's where the atoms are arranged differently in space. A key feature of an optical isomer is we need a carbon atom that has got 4 different groups of other atoms around it. We call this type of carbon a chiral carbon, or sometimes an asymmetric carbon, to indicate these 4 different groups without having to say it every single time. And so if we take a look at an example here, you can see this is the typical way of representing the spatial arrangement around a carbon atom. I've drawn my 4 bonds in the tetrahedral arrangement, pointing in the same plane here and here, and then we've got the bond that's coming out towards us and the bond that's going into the screen. So if we just have the elements hydrogen in the top position, and then say chlorine in the next position, and bromine and fluorine in this position. So we've got a halogenoalkane. And so this is one way of organising these elements around the carbon atom. Then, if we were to place a mirror to the right-hand side of this molecule and draw the image of this molecule as a reflection, at first glance, this looks like the exact same molecule. We still have the bromine atom coming out towards us and the fluorine going into the screen, and the other 2 bonds are in the same plane as the screen. However, if we were to rotate the right-hand molecule around, so the fluorine and the bromine were pointing to the right-hand side of the screen for both of our atoms, what you can see in the second example is that the bromine is this time pointing into the screen and it's the fluorine that's coming out. So we've ended up with the 2 atoms actually pointing in opposite directions in space. And you can see this firsthand for yourself when you put your hands together in front of you. You can see that your hands are normally pretty much mirror images of each other. Your hands line up nicely as I'm showing in this little Bitmoji here. But if you were to rotate one of your hands so the palms were both pointing in the same direction, you can see that these are very definitely not superimposable mirror images of each other. They are ish mirror images down the line in the middle, but they're not superimposable. And that's actually where the word chiral comes from. It derives from the Greek word which means hand, and that helps us to appreciate that we've got these hands that are mirror images of each other, but they're not superimposable. In the same way that, a pair of gloves, the gloves will fit on the correct hand and the gloves look the same, but they're actually mirror images of each other, and you couldn't put the glove for the left hand on the right hand because they are non-superimposable. These optical isomers are often referred to as enantiomers, and that phrase, enantiomers, encompasses both of the two different optical isomers, the two non-superimposable mirror images of each other. And when you draw them in exactly the same way that I've already said. You put the mirror in place down the middle, and to show that you've got two optical isomers, you just need to make sure you've got the correct tetrahedral geometry around each of them, and that the atoms that are coming out towards us for both enantiomers are the same, and the ones going into the screen for both enantiomers are the same. And here we have our two different enantiomers, which if we were to turn or twist one of them, it would not be the same as the other one. The spatial arrangement would be different. Before we can look at optical activity, we need to familiarise ourselves with something called plane-polarised light. Now, you will probably know that visible light can be considered to travel as a wave, and this wave can be considered as a transverse wave where the oscillations are at right angles to the direction of travel. But these oscillations might be up and down in the y plane, or they might be in the x plane if they're going perfectly side to side, or they could be in some combination away from the vertical and between the vertical and the horizontal. So it could be 45 degrees between the x and the y plane. Now, when you polarize light, what you do is you pass this light that's oscillating in all of these different directions through a filter which only has very, very narrow slits in a particular direction. So for instance, if the light hits a vertical filter, only the light which is travelling in a perfect vertical, so in other words in the y plane, can actually pass through. And we say it's been polarised because only the light which is travelling in a certain direction will pass through the filter. The filter could also be horizontal, and that will only let light through that is travelling horizontally away from the direction of travel. So in other words, it's oscillating side to side as the light travels along this line. You can explore the optical activity of a particular enantiomer by setting up the apparatus as shown here. What you've got on the left-hand side is some kind of light source where the light is being emitted in all directions. And then this light encounters a filter, which I've chosen to show as a vertical filter. So this will only let light travel through in one particular direction. And then it travels through a second filter, which is horizontal, and that only lets the light through that's traveling horizontally. And we haven't got any of that. And so what that means is this person that's on the far right-hand side of my picture won't see anything because the light has been polarised twice by two polarimeters which are set at different angles. Then if we put a sample tube between them that maybe is just full of water, for instance, we will still see nothing. This person will see nothing through that polarimeter. They won't know that the sample tube is there. If we take that water sample tube away and we replace it with a different sample tube which has got a sample of an optical isomer, what will happen is the light will be rotated slightly by this sample. And so what that means is a small portion of light will pass through the polarimeter on the right-hand side, and the person who is observing this experiment will see a little bit of light travelling through. What these polarimeters have is they have a dial on them that allows you to rotate the polarizing filter slightly, and you would rotate it until you could no longer see any light travelling through the filter. But what you would have to do is you would have to note the position of the filter before you started rotating it, and then you'd note it afterwards. And you would see, for instance, that maybe you'd rotated this filter 2 degrees in a clockwise direction. And the reason that you've had to do that is your sample is optically active and it has rotated the light as well. And so what you are detecting by rotating your polarizing filter is you're seeing, first of all, that your sample has rotated the light. It is optically active. That's what we mean by optically active. It has rotated this plane polarized light. But you're also seeing how much it has done it by, how much it has rotated this light, and in which direction as well. For A-level chemistry, you typically only need this knowledge that optical isomers will rotate plane polarized light. The 2 different optical isomers will rotate plane polarized light in different directions. So for instance, my left-hand optical isomer here might rotate the light 2 degrees clockwise. The other enantiomer on the other side will rotate it 2 degrees anti-clockwise. So they will rotate it by the same amount, but in opposite directions. Sometimes when you're investigating optical isomers, you might expect optical activity from a sample, but you might not get it. This will always be because the sample that you've put between your 2 filters is actually a racemic mixture. So in other words, this has got a 50-50 mixture of the 2 enantiomers. And that means that their 2 effects have cancelled each other out, because in a sample there'll be billions of these optically active molecules. They will be present in equal amounts in this racemic mixture, sometimes called a racemate as well, and so that means their effects will cancel each other out and the sample will not be optically active. In A-level chemistry, you need to know about how 2 different types of racemic mixtures form. They both form in the exact same way for the same reasons, but the one that I'm going to cover first comes up 9 times out of 10 if there's a racemic mixture question. And this is to do with nucleophilic addition to a carbonyl compound. If we consider the bonding around a carbonyl, let's make this butanone, the carbonyl carbon has got a planar arrangement around it. The bond angles are all 120 degrees. And so what that means is when a nucleophile attacks that carbonyl carbon, there is a 50-50 chance that the nucleophile could attack from above or below. Both are equally probable, and so both will happen in equal amounts. And so ultimately, when you get your product, you will get a 50-50 mix of the 2 products where the nucleophiles are different arrangements in space. Sometimes they might be pointing outwards towards us, other times they might be pointing into the screen away from us. The other example is in electrophilic addition to alkenes. And if we focus on the intermediate stage, where we have a carbocation, what we've actually got is we've got a carbon atom with 3 groups around it that is positively charged. These 3 groups around the carbocation will again be planar with a 120 degree angle between them. And so we're only talking about the carbon of the carbocation, not the rest of the molecule. That won't necessarily be planar, but the carbocation's carbon will be. And so what that means is the negative ion that's about to add on to this carbocation could attack from above or below, 50% chance of each. They'll both happen equal amounts, and so we'll end up with some of our, say, halogenoalkane with the bromine pointing out towards us, and others will be pointing away from us, 50-50 mix, racemic mixture. An interesting question to ask is, why does optical isomerism even matter beyond the fact that enantiomers rotate plane polarized light in different directions? Well, the answer is that the 2 different enantiomers sometimes have dramatically different biological properties. And this all comes down to the spatial arrangement of the sort of the three elements on the underneath of the tetrahedron. So if we look at them from underneath, you can see I've got three different circles on the left-hand side arranged as a triangle, and then if I had a slightly different arrangement on the right-hand side for an enantiomer, there is no way that I can twist the second one to make it look like the first. And so this is symbolizing the two different enantiomers. Well, there are some examples in nature, and there's other examples in the pharmaceutical companies. And so if we take a look at one example, which is called carvone, there is one enantiomer of carvone that smells like mint, and another that smells like caraway seeds. And so obviously you definitely don't want to mix those two up. Another example is something called limonene. One enantiomer of limonene is commonly used in cosmetics and shampoos and things like that because it smells of citrus. The other one smells of pine, and so obviously will have different uses. Beyond smells and tastes, there can be some really important biological uses in things such as enzymes. Enzymes, as you know, have very specific active sites, and that means that they have a particular shape. Not only that, the active site might have a particular sequence to its receptors on the surface. And so that means that specific molecules with a specific spatial arrangement, not just a specific shape, will be able to bind to the active site of the enzymes. And that's true in a lot of biochemistry. Another example of why optical isomerism matters is a really serious one that dates back to the 1960s, and that's to do with the drug called thalidomide. This was prescribed to alleviate nausea and morning sickness, but actually only one of the enantiomers did this. The other was useless in that regard. But worse than that, the second enantiomer was actually what's called a teratogen, which means it causes birth defects. So when this drug was given to pregnant women, the children were born with these birth defects that were completely unexpected. And so that's why it's really important to use enantiomerically pure drugs, in other words, that are 100% of one particular enantiomer, that will therefore give you 100% the effect that you're looking for. And there are other examples than thalidomide in medicine, but that's probably the most common in terms of discussion points. Some exam questions will ask you whether or not a particular compound is optically active, and if it is, to identify the chiral center in that molecule. Let's take a look at that concept now. If we take a look at this top molecule, what we're looking for as we work left to right is we're looking for how many different groups there are attached to this particular atom of carbon. And so if we take a look at the first one, you can see there is 1 hydrogen, 2 and 3. So that's definitely not 3 different groups. Again, on the second one, 2 hydrogen, so not a chiral center. 2 hydrogen, this one, 1 hydrogen and a bromine. Okay, this is looking promising. So there's our bromine, there's our hydrogen. We've also got this methyl group attached to it, and we can see that our last structure is definitely different as well. So we've ended up with 4 different groups around this carbon atom, and so the chiral center is this carbon. In the next molecule, we apply the same principle. The first carbon atom has once again got 3 identical groups attached to it. And then the middle one, well, this is looking promising again. We've got a fluorine and we've got a hydrogen. But then when we look at the side positions, the 2 groups to either side of this carbon atom are actually the same. And so this has only got 3 different groups attached to it. And so the second example would not be optically active as it does not have a chiral center. You can apply the same logic if you're given a structural formula, but it's a little bit harder. But this first situation, we've got CH3, so this is not an optically active carbon. Then we've got a CH2, so again, not optically active. You must always rule out any carbon that's got more than 1 hydrogen attached to it can't be optically active. So then we've got this carbon atom, which has only got 1 hydrogen attached to it. It's also got an iodine attached to it. So this looks promising. That's 2 different groups. And then we've got this methyl group attached to it, and on the left-hand side, if we look backwards, we've got this ethyl group attached to it. So this will be a chiral carbon because it's got 4 different groups. Sometimes it's helpful while you're looking at a question like this to give a sort of a mixture of displayed and structural formulae around that particular carbon. So you put your carbon that you think might be promising in the centre, and then you put each of the 4 different groups going off at kind of sort of 90-degree angles to each other, because we're not worried about geometry if we're just looking at whether or not something has a chiral centre. And so that allows you to see clearly that it has a chiral centre. Skeletal formula, you can still do it, it's harder still, but what you have to remember is we never show hydrogen atoms. So if we consider the left-hand example, there are 3 hydrogen atoms there, we're just not showing them. This one, there is 1 hydrogen atom. I'm going to add it in. Then if we look at the groupings, we've got this group on the left-hand side. We've got this group next. That's obviously different to the original. Then we've got the hydrogen that I've drawn. Then we've got the bromine. So this is optically active, and this will be the chiral centre, the carbon with 4 different groups attached. Last of all, we've got 3 hydrogen, 2 hydrogen, so they're no good. This one has got no hydrogen on it, but that doesn't mean it's not chiral. What it does mean, though, is we need to look at these positions. Here, this will be a carbon with 3 hydrogens. This will also be a carbon with 3 hydrogens. So this is not a chiral centre, and so there will not be optically active molecules of this type. By far the hardest type of question about is it optically active is when they just give you a formula and not any clues as to the structural arrangement of these elements. So if we first take a look at C6H12, does this ever have any isomers that exists as enantiomers? In other words, they are optically active. My strategy for working this out is to layer up your reasoning. And what I mean by that is, well, if it does have optical isomers, let's start with the central carbon that we think will be optically active. And then let's put our hydrogen atom in. And if it's optically active, it's probably going to have a CH3 group up here. And then if we put a CH2CH3 group, we're keeping it as simple as can be, and we're gradually adding more complexity as we've worked along. So if this was C6H12, what we're looking for is well, what else are we missing? Well, I've used 4 carbons, so I need another 2. I've used 9 hydrogens, so I only need another 3. So this carbon will be bonded to another carbon, which will actually have a double bond to another carbon, and it will have 2 hydrogens like so, and there we go. That is our proof that this will exist as optical isomers because we've got 4 different groups around our central carbon. And I really do strongly recommend you gradually working your way up. Have a hydrogen, have a methyl group, have an ethyl group, and see what's left over. Let's look at a second example, C5H11Br. Does this ever have any isomers that are optically active? Let's apply the same line of reasoning. Let's start with our central carbon, put the hydrogen in position, then the methyl group, and then last of all our ethyl group. And now we can start thinking carefully. What have we actually used? We've used 4 carbon atoms so far, so we need to add our 5th carbon atom. How many hydrogens have we used? Well, that's 9, so we need to put another 2 in position here, and then we need to add our bromine. So this is nearly not showing optical isomerism because we've got a CH3 and a CH2Br, but they are definitely different. So this does display optical activity because this particular isomer of C5H11Br that I've drawn will be optically active because this is the chiral centre. You can also get multiple choice questions about optical activity, and I will definitely release some of those soon. But for now, I think that's all for optical isomerism. I hope that was useful. I'll see you again soon.